Hello and welcome to lecture 20. In last lecture, we were discussing about the cycle analysis for ideal and actual two-spool turbojet engine with afterburner. We have discussed about the calculation of various cycle parameters when we are incorporating the afterburner. Then we also have discussed about the performance parameters for turbojet engine with afterburner, and we have tried to explore the difference between with afterburner case and without afterburner case. Now, this is what will be giving you the idea about how do we move forward with. Now, in order to understand what all cycle we have discussed here, we will take one numerical here. So, let us see, say we are having two spool turbojet engine with the afterburner, and for the sake of brevity at this moment we will be considering our ground condition. So, if you look at these numbers are similar to what all we have discussed as our two spool turbojet engine without afterburner, because we are targeting to discuss what will happen with say incorporation of the afterburner. So, if we look at carefully what all numbers we are having in terms of say pressure ratio for say LP spool, it is 3.35, say pressure ratio for HP, it is 4.65, turbine entry temperature is 1200, mass flow rate also we are considering as say 186 kg per second. All parameters we have considered to be same. Now, here in this case what we have done, we have introduced the afterburner. So, it says if the afterburner is operative, that is what will be reaching the maximum temperature of 1700 Kelvin. There will be 5% pressure loss which is happening inside the afterburner, and the efficiency of this afterburner is 95%. So, we will try to solve this numerical, and you will realize what is the use, why we are taking same information, same data as previous one, and now we are introducing the afterburner. So, just try to collect this information, just write down what all we know. So, let us try to discuss this part here, what all hint we are having. See, we are having different components. So, this is what is a strategical say steps. We can say very first component what we have is our intake or diffuser. That process we are representing as infinity to 0 2. For that we know what is my M infinity. Here in this case this is my ground condition. So, M infinity it is 0. My atmospheric pressure and temperature they are known to me, and diffuser efficiency is also known to me. So, we can calculate what will be my say temperature and pressure at the exit of the diffuser. Since this is what is two spool configuration, the next component what we have is LP compressor. So, the process we are representing from 02 to 03. Now, for this LP compressor we know what is my say compression ratio, what is the efficiency. If we know these two parameters, we can calculate what will be my exit pressure and temperature from the LP compressor. The component we have further, it is say HP compressor. The process it is represented in terms of 02 to 04, and we know what is our efficiency and what is my pressure ratio. When I say we know, just remember one thing, at the initial stage when we are doing our cycle analysis, basically these numbers we need to assume. So, say compressor efficiency, that is what we are basically assuming. Okay, same way the compression ratio what I am talking about, say LP compressor ratio, HP compressor ratio, that also we need to assume, because for the specific or special thrust requirement we need to have these numbers. Okay. For solving this numerical, these numbers they are been given, but when you are starting from scratch you need to have your database. That is what is available, maybe on online mode or maybe by referring the research papers or by referring the books, you will be getting some information, some numbers, and later on you can modify, rectify as per your requirement. Okay. So, when I say given data, just remember one thing, when you are doing your actual cycle or when you are doing your design for your engine, these parameters need to be assumed. Okay. So, here we are able to calculate what will be my exit pressure and temperature from the HP compressor. The component we have is our combustion chamber. For that process, it is represented as 04 to 05, and for that we know what is our burner efficiency, what will be the drop of pressure in combustion chamber, my maximum turbine entry temperature or exit temperature from the combustor. We know what is the calorific value of the fuel, and based on that we will be able to calculate the exit pressure and fuel air ratio. The component what we have next is my HP turbine, that is represented by process 05 to 06. For this HP turbine also we know what is a mechanical efficiency, turbine efficiency, and what will be my turbine entry temperature. Now, in terms of mechanical efficiency, again and again we are putting say the range in the terms of 75% to 85%. For the most modern engines, they are having this efficiency, mechanical efficiency, that is what will be in the range of 90%. So, from this HP turbine information, we will be able to calculate the exit pressure and temperature from the HP turbine. That will be the input condition for the LP turbine. Here in this case, we know what is the efficiency, what is the mechanical efficiency, and based on that we will be able to calculate our exit pressure and temperature from the LP turbine. Now, since we are having our component as afterburner, so this is where you will be having difference compared to your earlier cycle analysis, where we were not having afterburner. Here we are incorporated with the afterburner. Now, for this afterburner, just realize one thing, we know what is the maximum temperature, that is what we will be achieving at the entry of the nozzle. Okay. Now, calorific value of the fuel, that fuel will be same what we are using in our main combustor, and we know what will be say the pressure drop within the afterburner. So, we are able to calculate what will be my exit pressure and temperature from the afterburner. The component what we have is my nozzle. This expansion process, it is been represented as say 08 to 09. For that case, we know what is our nozzle efficiency. Based on that, we will be doing our calculation for the critical pressure. Then we will be comparing that pressure with the atmospheric pressure. Then we will be defining whether my nozzle is choke or unchoke, and based on that we will try to decide what will be our exit pressure. Once that exit pressure is known to us, we will be calculating our density, we will be calculating our temperature at the exit, and based on that temperature, static temperature calculation, we will be calculating our exit velocity. So, you can say this is what will be giving you the idea about the calculation of cycle parameters. When I say cycle parameters, be careful, we are talking about the calculation of say pressure and temperature. Now, once we have all this information with us, we will be able to calculate our performance parameter. These performance parameters are thrust, thrust specific fuel consumption, specific thrust, thermal efficiency, propulsive efficiency, overall efficiency. Okay. So, let us begin with what all information it is given to us. So, say this is representing my actual cycle on TS diagram. So, very first thing you need to do is to locate the stations. So, just make a line diagram like this and write down the stations here 1, 2, 3, 4, 5, 6 like this, and similarly you just highlight on your TS diagram. So, that will not make any confusion when you are doing your cycle analysis. Be careful, we are not solving at this moment, we are solving only one numerical, and that is what is say 2 spool configuration with afterburner. By the end of the course, or maybe once you are out from your graduation, you will be learning number of cycles, and for that all the stations are very important. Okay. So, be careful, make a practice, use your pen and paper, and then just try to plot this TS diagram, try to plot the line diagram. That is what will be building your confidence. Okay. So, very first component, as we have discussed, is my intake or the inlet. It is represented by say infinity to 2. This is what is representing my inlet duct. Since this is my ground condition, so my M infinity will be 0. Under that condition, my V infinity will be 0, and if that is the case, we can say my P02, that is what will be coming as same as atmospheric pressure. So, we can say our location, my P02 and P infinity will be on the same location. So, my exit pressure will be 101.325 kilopascal. In line to that, you can do your calculation for the temperature. In temperature also, since my M infinity it is 0, so you can say our exit temperature from the diffuser, that is what is same as my atmospheric temperature, it is 288.15 Kelvin. So, what all information it is given to you, just write down those informations carefully. Read carefully whether it is given with the ground condition or the flying condition. Suppose if you are considering say ground condition, my formulation for the diffuser, that is what will be different. When I am considering say flying condition, my formulation, that is what will be different, and there are high chances that you will commit a mistake. So, you can understand, if you are making mistake here in terms of doing the calculation, that will be carried forward till the last calculation. Okay. So, do everything carefully. Okay. Now, let us move towards the next component. The next component what we have is our LP compressor. For that, pressure ratio is defined, it is say 3.35. My efficiency is given 88%. So, based on the pressure ratio, we can calculate what will be my exit pressure, and this exit pressure is coming 339.44 kilopascal. Now, as we know, in order to calculate the temperature at the exit of the compressor, we will be using the formula of efficiency. So, this efficiency and pressure ratio, if we are putting together, since my T02 is known to me, my pressure ratio is known to me, efficiency is known to me, we can do the calculation for say exit temperature from the LP compressor. And if we put all these numbers, that is coming as say 423.25 Kelvin. Okay. Now, what next component we have, that is say my HP compressor. For HP compressor, we know what is our pressure ratio. It says my pressure ratio is 4.65. So, if I am putting that as my pressure ratio, we will be calculating our exit pressure, and this exit pressure is coming as a 1578.4 kilopascal. Be careful in terms of writing the units. Okay. In line to what all we have discussed for LP compressor, we can correlate our temperature and pressure with efficiency. That is what will be helpful to us for the calculation of my exit temperature. So, here this is represented as say compressor ratio of my HP compressor and my efficiency of the HP compressor. Okay. So, if we are putting these numbers, it says my T04, that is the exit pressure from my HP compressor, that is coming as 688.42 Kelvin. So, we are able to calculate the pressure and temperature at the exit of HP compressor. Now, the next component what we have is our combustion chamber, and for this combustion chamber, we know we are considering the ideal process as a constant pressure heat addition process, where my fuel and air will get ignited and that will be releasing the energy. So, we can say it is energy input or heat input process. In actual condition, it says we are given with say drop of pressure by 3%. So, let us put this loss of pressure, you can say my P05, it is exit pressure from the combustion chamber, that is coming as 1531.05 kilopascal. Okay. Now, here in this case we know what is our temperature. So, this temperature is nothing but my turbine entry temperature, and that is given 1200 Kelvin. Now, let me put this as my control volume, and I will be putting my mass balance. So, this mass balance, it is given by m infinity plus mf, that is what is equal to m infinity plus mf on the other side as a exit. Now, let us try to put this control volume in terms of energy balance formulation. So, here this is what is m infinity into H04, that is nothing but the temperature with which or enthalpy with which my flow will be entering inside the combustion chamber. This is what is representing by energy release during the combustion process, and at the exit we will be having m infinity plus mf, and this will be the rise of my enthalpy, that is H05. So, if we will be writing our energy balance, it says we are able to calculate what is our fuel air ratio. This fuel air ratio, it is correlated with the burner efficiency. So, let us put these numbers again. Here be careful what all units you are selecting. Suppose you are selecting your CP unit to be joule, then you consider all parameters to be in joule formulation. Suppose you are considering that into kilojoule, then carefully do it in terms of kilojoule formulation, else there are high chances that we will be making mistake here in terms of calculation for fuel air ratio. So, this number it is coming 0.0168. This is what is my fuel air ratio. Now, once the combustion chamber it is been done with, we have our next component, that is my HP turbine. So, the process we are representing in terms of process 5 to 6, and this expansion process we know this turbine it is been used to rotate my compressor. So, we will be doing our work balance, say my work required for the HP compressor, that is what will be provided by work developed by my HP turbine in with incorporation of my mechanical efficiency. Now, this mechanical efficiency what we are discussing, basically they are the losses which are happening because of my bearings. Okay. So, here let us put this formula, and by formulation we will be able to put my T06, it is nothing but the exit temperature from my HP turbine. So, if we will be putting these numbers, it says my exit temperature it is coming 933.27 Kelvin. Okay. Now, we know if we want to calculate what will be my exit pressure from the turbine, we have our correlation in terms of temperature, pressure and efficiency for the turbine. So, let us try to put this formula. It says by expansion ratio, that is what is given by in terms of temperature and efficiency. Here this gamma value, carefully look at, it is written gamma H, gamma suffix H, that is what is representing my hot gas. Okay. And for that gamma value it is given 1.3. So, let us put this in the formula. We will be getting our exit pressure as say 475.61 kilopascal. So, this is what will be my exit pressure from the HP turbine. Okay. Now, the next component what we have is our LP turbine. For LP turbine also we can say this LP turbine it is been used to rotate our LP compressor, and we are correlating that in terms of mechanical efficiency. So, we will be writing the equation of work balance here, and if we will be simplifying this equation, this is giving me the exit temperature from my LP turbine. Let us put all these numbers, because we know what is my T03, what is my T02, mechanical efficiency, fuel air ratio, Cp value, all this together, that is what will be giving me my exit temperature to be 797.4 Kelvin. Okay. Now, next what we have, it is for the calculation of the exit pressure from the LP turbine. So, we know pressure, temperature and efficiency, they are being correlated. This correlation, that is what will be giving me the pressure at the exit of our LP turbine. So, let us put these numbers. So, by putting this number, it says my exit pressure is coming 229.39 kilopascal. Okay. So, now up to here what all we have done, this is what is known to you, okay, because we have solved this numerical as in a previous case also for two spool configuration. Next what we have is our afterburner. So, in afterburner we have discussed, we will be having loss of pressure. It says there is a 5% loss of pressure which is happening inside the afterburner. So, if we will be putting this number, it says 0.95 times the P07 and my exit pressure is coming 217.92 kilopascal. Okay. So, be careful and just understand the logic here. This pressure and the pressure at which the flow is entering inside my main combustor, they are different. Okay. We have discussed this point in our earlier class. Okay. Now, for this we can write down our mass balance. We are interested in say our energy balance. So, here in this case the flow that is coming out from my LP turbine, it is having mass flow rate as say m infinity plus mf. We can say my fuel and air that together they are entering inside my say afterburner. This is what is representing my energy input because of burning, and here this is what will be coming out. So, you can say it is m infinity plus mf plus m dot fab into H08 AA. Okay. Now, let us try to write down this equation, and if we are writing this equation, it says we are able to write down the formulation for fuel air ratio required by the afterburner. Okay. And for this afterburner, since we know what is my fuel air ratio, we know what is my say entry temperature at the turbine, because that is given 1700 Kelvin. So, T07 we have calculated. My afterburner efficiency is known to me. For this particular combustor, my fuel calorific value is given 45,000, and this T08 A that is also known to us. Let us put this number, this all together it says my fuel air ratio for say afterburner, it is coming 0.026. Okay. Now, once we have done this calculation, our next component of interest is the nozzle. This nozzle expansion process, it is represented by 8 AA to 9 AA. So, here we will be doing our calculation for the critical pressure, since this is what is actual cycle and we have information about the nozzle efficiency. This nozzle efficiency is given as a 96%. So, we will be doing this calculation, and it says my critical pressure by calculation, it is coming 115.74 kilopascal. Okay. Now, if this is the case, we know our atmospheric pressure is 101.325 kilopascal, and if we are comparing, it says the critical pressure is higher than that of my atmospheric pressure. So, we can say my nozzle is a choke nozzle. So, when my nozzle is a choke nozzle, we can say my exit pressure is critical pressure, and this is 115.74 kilopascal. So, now we have information about exit static pressure. Okay. So, for this nozzle, we will try to calculate what will be the exit static temperature, because we are interested in calculating our exit velocity. So, here this temperature ratio is given by gamma plus 1 divided by 2, and if we are putting these numbers, it says my exit static temperature, it is coming 1478.26. Okay. Now, this is what is the exit static temperature which is coming out from the nozzle. Once we have this information, we can calculate what will be our exit velocity, and this exit velocity we are writing as a gamma RT9 AA. Now, this if we will be putting in the formulation, it says my exit velocity is coming as 742.66 meter per second. Okay. So, by this we are able to calculate our cycle parameters. Now, in next lecture we will try to do the calculation for the performance parameters, and as we have discussed in earlier case also, we will try to incorporate the change of my parameters like overall pressure ratio, turbine entry temperature, and how these parameters they are affecting my thrust, specific fuel consumption, specific thrust and efficiency term. That will give us idea how do we move forward with the change of parameter. That is what is required for my cycle analysis, or that is what is required for design of my gas turbine engine, specifically for the application of aircraft. And this is what we are discussing at this moment. It is with the afterburner. Okay. So, here we are stopping with, and in next lecture we will be doing our performance parameter calculation. Thank you very much for your kind attention.